morning. So this is a last lecture which is devoted to a topic that is a little bit advanced in some sense, although potentially useful, and therefore I would like to spend a lecture on it. It was suggested by one of you, so I very much appreciate that. It is what is called a semi-classical, or WKB, by the name of the three physicists who, this is Kramers, Brillouin, Werners, who formulated it. Well, they were probably not the first to formulate a similar thing, but in any case, it is associated to their name. The idea is the following. You remember, we had a simple case, the free particle. So if there is a constant potential, say V, in the free particle case, we usually set V to 0, okay? But suppose we set it explicitly to some constant. Then you know that there is, for energy greater than V, the solutions of the problem minus h bar square over 2m, second derivative, plus V psi equal to E psi. Oh, by the way, all this is in 1D, okay? It works in 1D and with some subtleties for the radial problem of a three-dimensional or two-dimensional thing. But there are some delicacies, okay? So in 1D, it's a quite general approach that you can think of using. Now, if E is greater than V, you know that the solution will be of the form plane wave, okay? Where K is simply such that h bar square K square over 2m is equal to E minus V, which is a positive number, okay? We have done this, and therefore K is equal to square root of 2m E minus V over h bar. Okay, on the contrary, if E is less than V, well, strictly speaking, there is no admissible solution in the whole space. Nevertheless, formally, the two solutions that you can think of, oh, by the way, this could be with a plus or a minus. If you take K to be just a positive square root, then you know that there are two waves, the wave traveling to the right and the wave traveling to the left, degenerate. In the other case, formally, the two solutions are e to the plus or minus some calligraphic k times x, okay? Where this calligraphic k is pretty similar to that object, where however, now we have v minus e, okay? So, in some sense, this is an evanescent wave, e to the minus kx, which you know it's good, for instance, if you have a barrier, something like this, okay, and you want to describe the wave here, okay, that is fine. The other one is an exponential increasing wave, is never allowed in any infinite region of space. Where it is allowed is in finite regions, okay? So if you want to describe, sorry, the evanescent wave, the potential would be something like this, okay? So suppose that you have a potential like that, okay, and the energy is this, then here, okay, this is a region where E is less than V, in principle, okay, suppose that this is constant, so you are in this situation, E less than V, so in this region, in principle, E to the minus kx is okay. E to the plus is never okay. The other case where you could have both is if you have, for instance, a barrier like this, okay? Whatever, okay? So in a finite region of space, the energy is less than V, then in principle, in that finite region, both solutions are okay. They do not never diverge, and therefore you should, in principle, allow them with two coefficients and do matching and whatever, okay? So this is the situation that we have discussed so far. Now, all this is for a constant, perfectly constant potential. What happens if the potential depends on x? Well, if it depends on x in a wild way, there's nothing else that you can do except for, putting it on a computer. But if it depends on x in a smooth enough way, which we'll try to specify, so it does something like this, for instance, okay? Something smooth, then maybe we can do something, okay? In particular, this is a wave. It's a perfect sinusoidal wave in some sense, okay? It's real part and imaginary part, but it's a perfect wave with a well-defined wavelength, okay, which is 2 pi over k, fixed. Now, you know that in radio signals, you can do two things. You can do amplitude modulation, AM, which means that the amplitude of a wave is slowly changed, okay? Let me not draw it, but you understand, okay? The amplitude slowly changes. Or, so this would be AM. Or frequency modulation, which means that the frequency slowly changes, okay? Like that. That would be FM, okay? So they're both very well used to encode signals on top of a main driving frequency, okay? So the first amplitude modulation is essentially the fact that this amplitude here would depend now on x rather than being just a constant, okay? The second is the fact that rather than being k times x, this in principle should be substituted by an integral from some constant, doesn't matter, to x, of some k of x prime in dx prime, okay? In other words, here, the frequency, the wavelength is no longer constant. If k is constant, you recover this. You get just the constant times x. The constant from this term can be reabsorbed in A. So it doesn't matter where you put the initial point of this thing. You shift everything and you reabsorb a finite constant in the amplitude, okay? So this would be something that would allow you to describe frequency modulation, okay? And this would describe for you amplitude modulation, okay? So let me write this in more general terms of phi of x, where I have in mind that in some sense the derivative of this thing will be related to k, to a momentum. By the way, k is also related to momentum, okay? In fact, let me define right away, okay? So suppose that I have this potential, V of x, and I have a certain energy. You know that the right energies for the problem will have to be found, okay, in this case, because this would be, for instance, a bound state. But to find the bound state, you have to tune the thing, okay, in a situation like this. Nevertheless, suppose for a time that I have some energy. We'll discuss the matching and the tuning later. Then in this region here, okay, which is classically, this is a region where classical motion can occur, okay? Classically, the particle would do like that, tack, 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 okay? So this is a classical region, while this is a region that is purely quantum in some sense. Only evanescent waves are allowed here and there, okay? So this is classically forbidden. All right. In the classical region, you can define a classical momentum, okay? So px squared over 2m plus vx should be equal to E, right? Classically. So the classical momentum, you can solve this, px squared is equal to 2m E minus v of x, okay? Or if you allow me to just draw here a square root and take the positive value, so the classical momentum is just well, plus or minus, depending if you're going right or left, the absolute value of it is just square root of 2m. You see that this is essentially this quantity here, okay? So this is also the classical momentum. All right. Oh, by the way, reference, it's in many books, obviously. You can look, for instance, in Landau, but perhaps you will be discouraged if you look right away in Landau. A good, rather elementary but very careful source is the book by Griffiths, Introduction to Quantum Mechanics, okay, chapter 8. And this is the source that I will be following, more or less. Okay, so let us now do the general case where V varies with the space. So I have in mind something like this, for instance. And then the equation that I should solve, I can write it in the following way. Bring V on the right-hand side, okay, and multiply by 2m over h bar, and the minus sign is the following. The second derivative is equal to minus 2m over h bar square e minus v of x multiplied by psi. Okay? It's totally equivalent to the, okay? So you see immediately that this is what? This is nothing but the classical momentum squared divided by h bar squared. Okay, so let me rewrite this as px squared divided by h bar squared. Okay? In some sense, this is obvious, right? The quantum momentum operator is, h bar, the gradient, okay? In some sense, the second derivative is indeed the square of the quantum operator momentum, okay, divided by appropriate mass terms. Do I have, okay. Yes. Okay, so this is all right. Let us try to solve this equation, which is totally equivalent to this, by an ansatz. Okay, so let us suppose that the solution is in the form of an amplitude that now depends on x times a phase that depends on x, but I expect that it will not be just quite k times x. It will be something related to this. Okay, so let's see. If I calculate the first derivative, so I put psi equal to that, and I calculate the first derivative of psi. What do I get? Well, let me indicate with the prime the derivatives so that things are easy. I have a term that is a prime, when I take the derivative of this, times e to the I, the phase. Okay? Plus, if I take the derivative of the exponential, I get I, a phi prime, times e to the I, the phase. Okay? I omit the dependence on x. It's implicit everywhere. Okay? So this is the first derivative. Then I have to calculate the second derivative. Okay? The second derivative is equal to, let's see, if I calculate another derivative here, I get a second, e to the I phi. If I calculate the derivative of the exponential, I get a term like that, right? Except that I do have now a prime. So I get I a prime phi prime e to the I phi from here. However, also from the derivative of a here, I get a similar term. So I get the factor 2, really. This is something that you have done perhaps many times. And then what? And then there is a term in which I take the second derivative here. So I a phi second e to the I phi. And finally, the derivative of the exponential, which brings another I. So with this, I get the minus sign, A, then I get the phi prime squared e to the I phi. Okay? I've just taken second derivative. Okay, good. Now, I put there. Okay? So let me rewrite everything. Will you allow me to, yes, to erase some of the stuff here? Why not? Okay. So I put this there. And I have, let me just copy so that I do it a bit faster. So I have a second. The exponential is everywhere, okay? So let me put it in front of everything. A second plus 2I a prime phi prime plus I a phi second minus a phi prime square. Okay, this is the second derivative here. And then I have minus equal to minus p square over h bar square, where this is the classical momentum, times psi, which is a e to the I phi. Okay? So you see that the e to the I phi has done now its job of providing whatever derivatives were necessary. And the equation now involves A and phi, the amplitude and the phase. Let us see. You see that this term, and this term are real. Okay? While this object has an I. Okay? So let us separate this equation into an equation for the real part and an equation for the imaginary part. Okay? If I do so, I get that a second minus a phi prime square should be equal to minus p square over h bar square a on one hand, and this object should be 0. So 2a prime phi prime plus a phi second should be 0. Okay? Until now, everything is exact, no approximation. By the way, you notice that this object here is also equal to the derivative of a square phi prime. Okay? If you take the derivative, you get the derivative phi second times a, yes, try, okay, if you multiply times a, you get this. So it's not an equal sign. Take the derivative of this. You get 2a prime, the derivative of this times phi prime, plus a square phi second. Okay? So this object is quite obviously related to this. Just multiply by an a. Okay? So if this is 0, this is also 0, because it's 0 times a. Okay? Now, what is the solution of this? Very simple. A squared times phi prime should be a constant. Okay? So out of this, you immediately find that a squared times phi prime is a constant. Let me call it square. Since it is a constant, let me call it constant square. Or implication that a is just a constant divided by the square root of phi prime. Okay? This is the first implication of this second equation. Exact. Okay? The amplitude should be a constant divided by the square root of the derivative of the phase. All right? Good. Second piece, this one. Okay? Now let me rearrange this. You see, this term has an a, and this is a second. So I can rearrange it as a second equal to a times phi prime square minus p square over h bar square, okay? Or by dividing by the amplitude, which is different from 0, in this way. Okay, still exact. However, you see, if I try to do everything now exact, I put a here, I should calculate derivatives, this becomes an horrendous equation for the phi, the phase. Okay, very, very complicated, and equivalent, obviously, in difficulty to solving the original problem. So there is no free lunch here, and one has to do approximations at some time. The approximation we will do is the following, that the dependence of the amplitude, okay, in some sense, well, I'll justify it, okay? This second derivative of the amplitude divided by the amplitude is a small quantity, okay? So the approximation I will do is that this is roughly 0, okay? If this is so, then the equation for phi becomes very, very simple, okay, in one shot. Why? Let me erase. Because I can write that phi prime square is equal to p square over h bar square. Remember, p is the classical momentum square. I mean, this object here, let me write it like that. Okay? Okay, so this quantity tells, for instance, that phi prime takes the square root is equal to plus or minus px over h bar. The plus or minus is due to the fact that when you take the square root of a square, there is always a possible sign. And the integral, the phi, is simply the integral up to x of phi prime, x prime in dx prime. I do not indicate the lower thing because that changes simply an additive constant. You know that in the integral you can always add any constant, which means that you can select the initial thing the way you want, but the derivative is regulated by the upper thing. So the derivative of phi would be just take off the integral and calculate the resulting thing there. Okay, so this is clear, well, but then this is equal to plus or minus 1 over h bar, the integral up to x of p of x, or p of x prime, in the x prime. Now, you realize that this is exactly the expression I had at the beginning. In some sense, this is k of x prime, because it's a p divided by h bar, okay? So is the k that I would use in the free particle case, but now just x dependent because of the potential being x dependent, okay? So the classical momentum divided by h bar integrated provides the phase, okay? That's the result of this simple calculation. The prefactor, the amplitude, is 1 over, let me just, okay? So apart from a possible sign, which in some sense, the square root of a minus sign is an I. So phases in front are free. You can multiply everything by any phase you want, I, square root of whatever. Okay? The important thing is C over the square root of P of X. Okay? The positive, say, positive momentum. Okay? Also the H bar, I don't care much. That would be on H bar. So the constant here is different from the constant there. Okay? Allow me this freedom. Okay, so end of this small exercise is that the ansatz has led me to the following approximate form: a constant divided by the square root of the momentum, the classical momentum, e to the plus or minus integral up to x of in dx prime of px prime. There is an I and there is an h bar. Okay? The plus and the minus, you can choose both, and in principle you can superimpose two waves, one with the plus and one with the minus, with two different coefficients in the usual way. Okay? They're both solutions, and therefore they're both usable. All right, so this is what generalize the simple plane wave. Okay? Amplitude modulation, frequency modulation. All right? Good. Now, well, one small comment. If you take the modulus square of the wave, you notice that the phase cancels and you get c squared divided by p. This tells, obviously, that the probability of finding a particle at a certain position is inversely proportional to the momentum. The faster you travel, the less it's probable that you find a particle there. Okay? This is a small comment to this. Now, the derivation I have given here is probably not the standard one. In the books, for instance, in Landau, you find more often another derivation, which I would propose to you as an exercise, if you like, is the following. To say that psi of x is equal to e to the I, some function of x, divided by h bar. Okay? This is the first starting point. You can always write a complex function in terms of e to the I, another function, obviously. Okay? Notice I didn't put any amplitude in front because this function is now complex. So could have a real part and an imaginary part, and therefore you can split and take out some amplitude out of that. Now, you can write with this ansatz here, plug into the Schrödinger equation, and you will find something for f of this form. Let me copy it. I, h bar, the second derivative of f, minus the first derivative of f square, plus the usual classical momentum, equal to 0. Okay? This is very, very simple to derive. Then, the actual idea of this semi-classical approximation in this case is to say that f will have a form of this type. So f of x is some zero-order term. You see that there is a 1 over h bar there, okay? So in some sense, you are thinking of having small h bar in some semi-classical way of thinking. Obviously, h bar is whatever it is, okay? But it must be small relative to the important quantity that appear in the denominator. So there is a quantity that is f of 0x plus h bar times a first-order correction plus h bar square times a second-order correction plus, okay? So it looks like you are expanding f in powers of h bar. And the first term has 1 over h bar. The second term, h bar cancels. The third term, h bar appears now in the numerator, so it looks like a small correction, and so on. And you can find the equation for this, and recursively, in principle, for any other thing in an approximate and recursive way. And if you stop here, you get exactly something that is this solution here. Okay, this is the more standard way of doing the approach. It has the advantage, perhaps, of showing, in some sense, the role played by h bar in a kind of semi-classical expansion. This other approach is it's quite physically nice, having amplitude and phase varied in a slow way. Okay, so you can try to do this other approach, and you will have the more standard thing. Okay, so let me just do a simple exercise where I immediately can make use of that. Oh, by the way, before I erase, no, I will make this comment later, okay? So I erase whatever is not necessary here, okay? Okay, this I can erase. Perhaps here I can erase. Now, suppose that I have let me write this here. So psi of x is ax e to the I phi plus or minus phi x, which is now approximated to c over square root of px e to the plus or minus I over h bar integral up to x in bx prime of px prime. Okay? Good. Suppose that I want to do the following problem. The usual well, okay, where, however, now, rather than having, so the well, infinite potential here, but rather than being just a flat zero potential is some smooth bottom, okay, something like this, okay? So the potential in the middle is a smoothly varying bottom of the well. And I would like to know something about the states in this well. Well, the wave function has to be 0 here and there, right? While in the middle, we'll have this form. In principle, we'll have the form of two possible waves. I will write the wave function here as c plus over square root of px. So the energy is here, is higher than v. E to the plus I over h bar, the integral of px prime. In fact, let me write this as again as phi, okay? So that I write less things, okay? This is phi. This integral of object, okay? I call it phi again, so that I don't have to write too much. Plus c minus e to the minus I phi, still with the square root of px, okay? C plus and C minus are two arbitrary coefficients. And you realize that rather than using e to the I and e to the minus, I can always rearrange them into, this is obviously psi roughly equal to. This is an approximation. I can rewrite this as 1 over square root of p of x times a constant C1 for the sine of phi of x plus a constant C2 times the cosine of phi of x. Okay? I can always do that. Good. Now, let us look. Phi of x, okay? Apart from a constant, I can always rewrite as integral from 0. 0 is my origin here, to x of px prime in dx prime divided by 1 over h bar. Okay? Now, with this choice of the initial boundary thing, the phase in 0 is exactly 0. And this term is fine because the sign of 0 is 0 there. Okay? This immediately tells you that, as in the problem of the square well, which we did with this choice of interval 0a, I can just get rid of this. And this is the one that satisfies the correct boundary condition. So I have to take C2 equals 0 to satisfy the boundary condition there. Good. Then the wave function, while being equal to the sine of this phase, must also go to 0 there, right? So I must fix the fact that the sine of the phase in A now has to be also 0. Good. Which immediately tells me that the phase in A has to be a multiple of pi. where n should be 1, 2, and so on, an integer. Not 0, because otherwise you would have phase 0 everywhere, which is zero-wave function, nothing really useful. Okay? Well, this is a very nice equation now, because take it together with that, it tells me that 1 over h bar, the integral from 0 to a of the classical momentum in dx prime should be equal to n pi. How cute. Okay? So the energy is contained there, because if you remember, the classical momentum is essentially, this is px squared over 2m, the kinetic energy, right? This plus v of x is equal to E, okay? So the energy is contained in there, okay? And this is a quantization condition, all right? Only the energies such that the integral of the momentum in this region is equal to a multiple of pi h bar are allowed, all right? And I had no idea of how to solve this potential v of x exactly, okay? It is in some sense a cheap way of obtaining information on the allowed energies without actually solving for a possibly complicated v of x, which is, however, smooth enough that I can do the approximation. I still have to do a bit of comment on this smoothness, okay? Wait for a second. Okay? So is this clear? Obviously, if you do the original case, so v is equal to 0, you can immediately find that this recovers exactly the exercise of the square well, okay? So if v is equal to 0, then p is equal to simply the square root of 2m e over, that's it, okay? So this is square root of 2m e, and therefore you have essentially, this is no longer a quantity which depends on x. The integral is simply a, so you have 1 over h bar square root of 2m e times a is equal to n pi, okay? And if you solve this, you will obtain the usual En equal to whatever h bar square, n square, pi square over whatever 2m a square, okay? I'm writing it very, very small, but okay, the exact result of, you might ask, how come something exact comes out of, I mean, an approximate thing? Well, you realize the miracle is simple. The approximation was in neglecting the fact that the amplitude was changing, actually. But indeed, in this case, the amplitude would not change. So in some sense, what appears here as an approximation is really exact in that potential case, okay? So, I mean, it's a miracle that is justified by a priori, in some sense. But this is nice, okay? So now, even if the potential is not perfectly constant, you can still calculate things. For instance, one very nice, well, this requires a little bit more. More about this later. Comment. Where I should apply this. In some sense, for what I've told you now, the wave function was valid in this form, okay, which is approximate, everywhere, including the borders here, okay? Because in some sense, everywhere, the momentum was kind of very large and defined. But now consider the following situation, which was the situation I depicted before. So the potential now does something like this, okay? And this is the energy. Now you see this is the momentum square over 2m, which changes and goes to 0 at the classical inversion point, x1, x2, okay? So you immediately realize that those are dangerous points. Why? Look at what appears there. 1 over square root of the momentum. Okay? So the wave function really diverges there. Very, very dangerous places. Okay? So the expression I wrote is okay inside here, but should not be really prolonged and used close to those classical inversion points. Okay? So these are dangerous regions. We'll take care of them in a second. All right. Now, second comment. What is this condition of this being small? Let us see more in detail. You can calculate, given the fact that A is given by a constant divided by square root of momentum, you can calculate what is, for instance, A prime. Okay? If A is equal to C over square root of P, immediately derive that A prime is equal to C times minus 1/2 P to the minus 3/2 P prime. Okay? Just a simple derivative. Then do a second derivative. And you get two possible terms. The first is if you derive this, and you get C times minus 1/2 times minus 3/2 P to the minus 5/2 times P prime, which then becomes square because of this term. Okay? And then there is an extra term that is plus C times minus 1/2 P to the minus 3/2. Now I take the derivative of that, so second derivative of P. Okay? So this is the second derivative. Now let me calculate second derivative over A. Okay? So second derivative over A is equal to this object divided by this. Okay? So the constant disappears. A square root of P also cancels with the sum of this P, and you get the following. You get essentially 3/4 P prime square divided by P square minus 1/2 P second divided by P. Very, very simple algebra, okay? The 3/4 comes from here. This is P to the minus 5/2, but divided by square root of pi becomes P square. Here you have P prime square, and in the second, P second divided by just P, because some square root factor cancels the 3/2. Okay? Good. So this is the quantity that I put to 0, really, in my approximation. Now, notice that close to the inversion point, the quantity that is really more, nasty is this, because it has a factor P squared. So this is really more important than that. Okay? So let us just drop this. Also, you see that the momentum involves the potential. Okay? This is somehow the first derivative of momentum, while this is the second derivative. So you realize that the second derivative is probably smoother also. Never mind, in any case. So let me drop this, and let me just consider this. Okay? So I want this object to be small. Small with respect to what? Well, it must be small with respect to this and that, for instance. Okay? So the momentum square has to be a large quantity. The phi prime square has to be a large quantity, and both should essentially almost cancel, apart from something that has to be smaller than both. Okay? So the condition that I have to write, in some sense, for the validity of this picture here, is that this quantity here allow me to drop the 3/4. So the fact that P prime square over P square should be much less, for instance, than that P square over H bar square, or phi prime square. Okay? This is this. Phi prime square, to a first approximation, is exactly the same, obviously. Okay? So this is the quantity that I should make sure is I mean, is small with respect to that. You shouldn't say with respect to 1, obviously, because you see that this is momentum divided by length. So this is 1 over a length square. So it should be small with respect to 1 over a length square, which is what? Is the wavelength, okay? Is the classical wave, I mean, the de Broglie wavelength of the wave I have, all right? So let me actually do a little bit of algebra. If I calculate this p prime, if p is equal to the square root of blah, 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 so p equal to the square root of 2m e minus v, you can immediately derive that p prime is equal to minus m v prime, the derivative of the potential, divided by square root of 2m e minus v. Very, very simple derivative, okay? With that, you can also recast this quantity here as, you see, I have the square of this, so mv prime square divided by, essentially this is, again, the momentum. So divided by momentum square times another momentum square, much less than the momentum square divided by h bar square. Now let's see if I can get everything correct now. So first of all, let me take, there are too many squares. Let me take here a square root of everything, and let me also invert the quantity, okay? So I have, let's see, the momentum square, first of all, as a factor 2m. So the momentum, this quantity here is 2m e minus v squared, this quantity here. Okay? So you see that the mass actually disappears. Okay? So what I have is that this quantity is v prime square divided by the factor 4. I don't care, as I didn't care about the factor 3/4. E minus v squared. So this should be much less than the 2m e minus v divided by h bar square. Okay? So I put here the expression for p, and here the expression for the derivative and whatever I needed. Okay? So this is the condition that should be always verified. Let me write it a bit more physically. So take the square root and invert. Okay? So from here, if you take a square root of every term, you can write that E minus V divided by the derivative of the potential, okay, should be much greater than H bar divided by 2m E minus V square root. Okay? So what is this? H bar over the momentum. Okay? So this is essentially the de Broglie wavelength. Okay? This is a length now. This is a length because it's energy divided by length. So this is a length. So the length over which the potential varies has to be much larger than the wavelength over which the wave itself varies. Okay? So amplitude modulation is, justified if you have several oscillations and slowly you change the amplitude. Otherwise, it's not an amplitude. Okay? So this is the condition. And you immediately see that this is never, never, never verified whenever E is equal to V at the classical turning point. Because there, the length, the de Broglie wavelength, diverges simply. Cannot be smaller than the length scale over which the potential. Okay? So this is, again, to reinforce that in the approximation, it was implicit that we stay away from the classical turning points. Okay? Those are the dangerous places. All right. What about evanescent places? Okay, so until now, I derived an expression in the region that are classically allowed. What about those? Yeah.
Is it just a mathematical consequence, or does it have some implication of those regions, x1 and x2?
So the question is if this is just a mathematical concept, or, I mean, this is, these are places where the approximation I have used is certainly bound to fail, okay? Because of a very simple, very simple consideration on the momentum, that classical momentum will go to 0 there. I mean, you immediately see it from the answer already. The answer is a 1 over square root of something that diverges. You know that the quantity, the psi doesn't diverge there, okay? So it must be wrong. And it is wrong because the approximation was to neglect this term. But this term is exactly equal to this. And if I do a little bit of manipulation, is essentially this. So first derivative divided by that. Now you see immediately that when this is equal to 0, you're not allowed to neglect anything. Okay, this is in fact large. It's even larger than that, which on the contrary becomes 0 there. Okay, so in some sense it's a mathematical inconsistency of the approximation. It tells, no, you cannot use this from here on. Okay? Now, if you stay away from those points in both regions, you can find, for instance, in this region here, another perfectly allowed semi-classical description. Okay? So in some sense, I should do the same algebra now on the region with this, that is classically forbidden. The algebra is very, very similar, except that now wave functions are real. There are no i's there. You can do exactly the same algebra. I guarantee that you do have essentially still an expression for momentum, but the momentum is now imaginary. So take just the modulus. So whenever I write now the momentum, you should imagine the modulus of the imaginary momentum in the usual way. And you can derive also for the classically forbidden regions expressions that are c over square root of modulus of p of x times e to the plus or minus, no I now, 1 over h bar, things like this. Okay? Identical, formally identical result, except that you now use no I and the square root of the momentum in the classically forbidden region, which has obviously only meaning in modulus. Okay? Now, this can be also obtained in a very similar spirit to what I did. I will not do it again. But now comes a problem. So I essentially know reasonable expressions here, okay, in these evanescent regions, okay, reasonable expressions inside the classical regions, but the whole region classical, close to the classical turning point is a dangerous place, okay? Both expressions are not valid in that region. So what do I do? I mean, usually when you were doing problems to find bound state, you were matching wave functions, okay? Exactly at the points where the thing was changing. Now, I cannot match anything here in this way because the wave function is not of this form close to the point. So there must be some way to circumvent this evident difficulty. Without a solution to this problem, these expressions are almost useless for bound state problems because I wouldn't know what is the exact energy for which the matching occurs. All right? Now, the solution to this point in the books is done in two possible ways. Both are not elementary, I must warn you. There are two possibilities. The first one is more mathematically driven, and is to say, okay, in the region close to the turning point, the potential, I can approximate it to a linear potential, okay? And therefore, if I do so, I would know how to write an exact expression for a linear potential, because I can solve the linear potential problem. It's known that this linear potential problem can be solved. In fact, this is the simplest problem in classical mechanics. Linear potential means a constant force, okay? Gravitational field. You drop something, you know how to calculate. In quantum mechanics, it's not that simple, but it is solvable. The solutions are called Airy functions, okay? I don't go into details because I don't want to do this way, okay? But it can be done. It's done in Griffiths, in every detail. So the solution inside here can be obtained in terms of two Airy functions, okay? Now, you can match, essentially, the solution here with the semi-classical approach to the Airy function here, and then again to the other semi-classical approach, okay? And in this way, you get somehow a bridge over the difficult region through, this certainty of an exact solution, all right? So in some sense, the bridge allows you to connect the coefficients of the, after all, you have two possible waves, for instance, here, okay? Well, you should eliminate the one that is meaningless, whatever. In fact, for if it is in this region, you want to have, you want to make sure that the quantity goes to 0. So choose the appropriate sign, whatever is needed. Then you match that coefficient to the coefficient inside, and then you match the coefficient inside to the coefficient outside again through these two patches of Airy functions. And in this way, you get definite relationship. Let me write the result, okay? Then I comment on a second way of doing the same exercise, which, however, requires a Russian-minded attitude, because it requires, essentially, to go in complex plane in such a way that you avoid this point, okay? Essentially, this is the place, x1 or x2, where the potential goes equal to the energy. Well, then you stay away from it, and you circumvent it in complex plane, okay? But in this way, this is what Landau does, for instance, you are able to connect a point far away from it on this side to a point far away on the other side in a way that is always far away from the dangerous point, because it passes through the corridor aside, okay? Which is complex plane. So this is more Russian type of approach. Doesn't use Airy function. It is, in fact, easier in some sense, although more mind-boggling, okay? So neither of them is particularly easy to explain, but let me give you the result, okay? Then we comment maybe a little bit more. The result is the following. Okay, if I have consider first this point here, x2. I need some space. Make space. So the wave function, so I have now region 2, region 3, and region 1. Okay? Now, psi I'll write it again for you, is roughly equal to 1 over square root of px in region 3, okay? So the evanescent wave to the right, times some coefficient that is called d, for instance, and then e to the minus integral 1 over h bar, integral from, say, x2 to x in the x prime of px prime, okay? So this is the evanescent wave that I wrote here, explicitly adapted to this point. So I write the integral from x2 to x, and I choose the minus sign because the plus sign would just diverge, okay? Then, in principle, in region 2, sorry, I wrote this a little bit too high, and therefore there's not much space there. So let me write it e to the minus 1 over h bar integral. Okay? So in the other region, in principle, I do have 1 over square root of px, region 2. And then I said it's a combination of e to the I over h bar integral from, say, x to, well, whatever, from x2 to x of p x prime in the x prime, and another piece that has the opposite sign. Let me write, since x2 is now certainly greater than, I write this way, so that in this way the integral is certainly positive, because x is less than x2 in that region, okay? x2. It doesn't matter, obviously. It's a matter of, I mean, this convention can be reabsorbed in coefficient and things like this. In principle, you have two constants here. Let me call it b and c. Now, as a result of the patching Airy function or going through the complex plane, you can derive that these two coefficients are related to that. In particular, you can prove that this coefficient here, for instance, is equal to d times minus I e to the I pi over 4, okay? And this coefficient here is equal to d times I e to the minus I pi over 4, okay? So the two coefficients are no longer free. They are related to d. However, there are phases, okay? And these phases are important, obviously. And the exact choice of these phases is as follows. So in particular, notice the e to the I pi over 4 and e to the minus I pi over 4. You might ask, where do they come from? Well, a Russian-oriented mind would immediately see that they come from the square root of p in the denominator. Because in going through the complex plane, okay, this 1 over square root of the 0, you change a phase by pi, you have a 1 over square root of a 1 over square root, because p is already 1 over square root. P is already the square root of 2m e minus v, okay? So it's square root of the 0. Then there is another square root, so it's the fourth square root, okay? And in doing a pi transversal, you get a phase e to the pi over 4, okay? So they come from analytical continuation of this object here. In any case, be what they are, okay? If you adopt one of the two techniques, you can match exactly the coefficient here to the coefficient there, okay? But the exercise requires a bit of care, and the exact result is that, okay? So let me just rewrite this, okay? I can just write as d over d over square root of px, okay? And then I have what? I can reabsorb the e to the pi over 4 here. So I can write e to the I 1 over h bar integral from x to x2 in dx prime of px prime plus pi over 4, okay? And the other one has exactly a minus sign, and this one has a minus I, okay? And the other one has a plus I, so you immediately tell me what it is, okay? It must be a sign, right? Okay? This is exactly what appears there, written explicitly. Now you see that this is essentially given by, so you write this as cosine plus I sine, this as cosine minus I sine. You multiply together, and you find that this is equal to d over square root of px times, let me just not do just a second. So I don't find the expression, so let us derive it, okay? So this is the cosine eliminates. The sine is minus I times I is, okay, so there is a sine, and there is a factor 2, right? 2d, the sine of this expression. So 2d, the sine of 1 over h bar, integral from x to x2 in dx prime px prime, okay, plus pi over 4, okay? If you look in Landau, you find it pretty similar, except you find written as cosine of minus pi over 4. It's the same thing. So you can rewrite as cosine with the plus pi over 4 or cosine with the minus. All right? So this is the expression in the classically forbidden and in the classically allowed. Now, matched. Notice, matched not at the point, but matched staying away from the point in a very careful way. All right. You can do a similar thing from here and there. So you can write a similar connection formula for region 1, okay? So if in region 1 you write the equation as d prime over square root of px times e to the minus now 1 over h bar integral from x to x1 px prime in dx prime. Why the minus? Because in this way the integral is now positive. I write as x to x1. X is before x1, so this is a positive thing, and this is an evanescent wave. Okay, so this is in region 1. Now the connection formula once again fixes the two terms inside here in terms of d prime, and you can prove that this is equal to 2 d prime over square root of px sine of 1 over h bar integral from x1 to x px prime dx prime plus pi over 4. Pretty similar, okay? What it changes, however, is a few details. Here I have integral from x to x2, and here I have integral from x1 to x. Obviously, the two expressions have to be perfectly consistent, right? So the expression for region 2 written in this way or written in this way do not have to clash, right? And there is a specific condition for not clashing, okay? Let me just explain this, okay? So the first one, which one? This one, x to x2, let me write as theta 2 of x. Okay? This expression here is the sine of theta 2 of x. Now, the expression here, let me insert the minus and the minus. Okay? So let me write this as the sine of theta 1 of x, where theta 1 is this object here. So minus 1, the integral from x1 to x plus pi over 4. Okay? I can always do that. Now, in order for the two expressions to be exactly the same, in one, I remind you, I have sine of theta 1 of x. The other one has the sine of theta 2 of x. What condition would you write for theta 1 and theta 2? Well, one would write something like theta 2 should be equal to theta 1 plus possibly some multiples of pi. You might say, okay, just a multiple of 2 pi. No, in fact, a multiple of pi is already okay. If the two signs differ by a multiple like 1 pi or 3 pi, they would have a different sign. But the sign is not important. You can always reabsorb the sign. Okay? So as long as they differ by a sign, they are still all right. So it's actually n pi rather than 2n pi. Okay, let us write the condition theta 2 equal to theta 1 plus n pi. Okay, I'll write it here. So theta 2 is the integral 1 over h bar, the integral from x to x2 px prime dx prime plus pi over 4. This is theta 2, should be equal to theta 1, which is minus 1 over h bar, the integral from x1 to x px prime in dx prime plus, minus with a minus, so minus pi over 4 plus n pi. Okay, so bring everything on this side, and you will have that this becomes a pi over 2. This becomes 1 over h bar, the integral from x1 to x plus the integral from x to x2. Okay, that's the reason why I decided to put a minus sign, so that when I bring on the other side, I reconstruct a full integral from x1 to x2. Okay, small trick. Okay, so this is the integral of the two pieces plus pi over 2 should be equal to n pi. Okay, let us rewrite it a little bit better. This tells me that the full integral from x1 to x2 of px prime in dx prime, so the integral of the classical momentum in the classically allowed region, divided by h bar should be equal to n minus 1/2 pi. Or if you multiply by h bar, there it is. Okay? So in order for these two different matching to be absolutely consistent inside the classical region, you must satisfy this condition. Now, you probably have seen this as Bohr-Sommerfeld quantization condition. You take a classical problem, you write the integral of the momentum, which is related in some way to the period of the time, classical time to go back and forth, and only the orbits, the classical orbits for which this integral momentum is a certain multiple of h bar are allowed. Okay? Well, this is now in some sense derived as a condition for having bound states in this semi-classical approach. Okay? And similarly to what we did for the square well with the soft thing, you can try to do several other problems now with this quantization condition. Notice that, by the way, the larger is n, so the larger is somehow the momentum, the more obviously the wave oscillates, but the more, in some sense, the this semi-classical approach is justified. So you expect that this, the bound states that you find from this approach are increasingly good as you move higher in n, okay? Because in some sense you oscillate more. It means the wavelength is smaller, and you want a potential that that changes slowly with respect to on the scale of the wavelength. So the higher is n, the higher is the momentum, the smaller is the length. So things improve, okay? Typically improve. For instance, I mean, there is a quite remarkable exercise. You can do the simple problem that I was mentioning before, dropping a ball, okay? What is the potential, if I call x this is the earth, the floor, and this is x, okay? What is the potential energy for a ball of mass m in the gravitational field of the earth? Well, infinite potential here, you cannot penetrate the floor, and then a linear potential there, okay? mg x. So that the force is minus mg, directed downward, okay? So this simple potential, I mean the simplest of all potential in classical physics, is rather complicated in quantum mechanics. As I told you, there is an exact solution in terms of Airy function. But I mean, you should consult books to find it. Nevertheless, you can find now what are the bound state of this problem by solving this, okay? And it's amazing how good they are, okay? If you solve this with this very simple thing, I mean, after all, this is now an integral of px. P is a very simple quantity. The integral is absolutely elementary. You can do it, okay? So no special functions, no books needed. And you find the energies of the first, say, 10 levels. Then you go and you check against the exact solution. At level number 10 is already perfectly smacked on, okay? But even the first few are essentially correct, okay? So this technique is guaranteed to improve in its goodness as you go higher in n, but sometimes it's surprisingly good even for rather low lying bound state, okay? And in any case, provides a very formidable tool to predict bound states for problems for which the analytical solution would be very, very complicated or sometimes impossible. In this case, it's just complicated, but in some cases, it's even impossible in terms of very elementary integrals that you have to do. Okay? So let me summarize. We derived in a specific approximation, so the potential varies slowly with respect to the wavelength of the particle. Expressions valid in classically allowed and classically forbidden regions. They are of the form of the standard plane waves with just amplitude modulation and frequency modulation. And I just gave to you as a result that there are matching conditions that you can do between these evanescent waves and the propagating waves, okay, at the dangerous points that, as I mentioned, are the classical turning points, okay? Those matching conditions can be derived in two ways, either with Airy functions or with this complex going into complex plane. Whoever is interested later on, I mean, I can explain to you the complex integral technique, but I don't find it particularly illuminating. That has to be necessarily understood. You just remember that there are ways of matching the coefficients there and there with that, okay? And with this, then you can actually solve problems like what are the quantization conditions for the energies in a potential like that. You could solve also the scattering problem. You could solve the other possible situation, like this. Suppose that you have a barrier that is now not usual square barrier, but something like this, for instance, okay? Some large barrier, smoothly varying like that. And you have some particle with energy E, okay, which is injected from the left, okay? Now, something will be reflected and something will be transmitted. How much is the transmission coefficient, you could ask. Now, unfortunately, you cannot do the usual exercise with the matching. But you know that here I have a classically forbidden region, so I have semi-classical expression of this form, plus or minus that. Here I have a semi-classical expression of the form of a running wave plus a reflected wave, pretty much like an expression like that. And here I will have a transmitted wave, pretty much like, for instance, like this, okay? E to the I plus integral from, say, x1 to x, where is it? Something like this, okay? Without the sign, e to the I plus that. Now, I can do, again, matching, and I can rederive what is the transmission coefficient. Okay, let me just sketch for you what you get. The wave function here is some oscillatory function, okay, with a pretty large amplitude, which is the impinging amplitude, okay? Then, well, let me just suppose that this ends here. In this region here, the wave function really decays, okay? And decays until it becomes very small, exponentially small, and then starts going again. This is the transmitted wave, okay? So, impinging, reflected wave, evanescent wave in the middle, and then transmitted wave. Now, how much the wave is depressed in this region is essentially due to this exponential factor here, okay? So if you want to know how much is the wave here smaller than the wave here, the answer, you can calculate with all the matching, but the answer is essentially e to the minus the integral from x1, say x1 is this point, x2 is this point, the integral from x1 to x2 of the dx prime square root of p, no square root here, px prime, okay, 1 over h bar. This is the amplitude. If you want to know the transmission coefficient, so the t square over t square, is e to the minus 2 that, 2 times that, okay? So this would be what the semi-classical expression tells you for the transmission coefficient wave. Is e to the minus exponentially small, the integral of the momentum, well, the modulus of the momentum, okay? Because the momentum is really negative there, I mean, imaginary, okay? Integrated over all the barrier, and with this factor in front. Now, this very simple expression allows you to solve problems. For instance, Gamow in the 30s solved the problem of predicting what the decay time of some radioactive nuclei would be. He made a model like that. The potential, so the nucleus is unstable, okay? And it separates by emitting some, say, alpha particle, which is essentially a nucleus of helium, for instance. It's a charged object. So when it separates and it goes away from, you know that there are nuclear forces that hold things together, that are stronger than Coulomb forces. So when you are at short distances, those forces are effective. Once they separate, however, the nuclear forces are no longer strong. They actually vanish, essentially, while the Coulomb forces are always there. And therefore, once they separate, they do something like this, okay? 1 over r, Coulomb force. So this is the separation between, say, the rest of the nucleus and the alpha particle that is emitted, so R. Okay? So Coulomb tail. However, for very small distances, there are attractive forces that are nuclear forces. So he made a model, say, okay, the potential that this particle feels is essentially deep, attractive object, but then there is some Coulomb tail. Now, if I want to have some particle with an energy E, okay, so I reveal an alpha particle with some energy E. This has gone through this barrier, okay? What is the T square that I have? Well, integral, as you see there, over this region. So by just modeling a little bit this, he was able to fit very remarkably the energy dependence, for instance, of the alpha particles emitted by several nuclei that were decaying. Okay? So this is a typical application of this formula in nuclear physics, Gamow model. All right, I think that this is, well, no, maybe we can still do a small, very, very simple exercise just to show you the Gamow theory is 1928. What else? Well, a simple exercise could be, for instance, potential like this. Let me find it for you. Okay, here it is. A potential like this. So let me draw. So the potential is infinite here. And here is some smooth enough object like this. Okay. A particular case of it would be, for instance, that here you have a quadratic potential. So it's the harmonic oscillator, but cut in two. Or any other smooth object like this. Now, in this case, you can play, for instance, and apply the formula, and what you would have is that, let me just, that the integral from 0 to x2 of px prime in dx prime, which you can calculate, is, I mean, something like whatever. I mean, given the potential, you can calculate this. This should be equal to the quantization condition. Let me just find it for you. Okay. You might be tempted of saying, okay, we do already have the matching condition, so why don't you apply? What I did there, however, was the quantization condition where two regions are both needed of a matching, okay? This brought some factors n minus 1/2, if you remember. Now, there are other cases where in this region there is no need for a matching because in some sense the potential, the P, remains large all the way, and what you can write is therefore that the phases goes to 0 there, exactly as we did in the example before. Okay? There is no need for a matching. So the only matching has to be applied here. So one condition only has to be used, this one. And this brings a slight variation. You get n minus a quarter pi over h bar, okay, rather than half. Doesn't make much of a difference because in some sense this is more apparent than really substance. The real place where these things are applied is when n is large. So small n, one has always to be cautious. So minus 1/2 or minus a quarter might seem different, but if n is large, it doesn't make any difference. In any case, this would be the expression if you apply, the quarter is due to this pi over 4. So if you apply the matching condition there, as I have written before to you here, and you finally get this quantization condition, this would allow you to solve for the energies of this potential here. So suppose that you now do the half harmonic oscillator. Then you can calculate this because the integral is elementary. And believe me, the calculation is simply pi over 4 m omega square x2 squared. This is x2. Okay? Which you can calculate in terms of the energy for the harmonic oscillator case. It's pi e over twice omega. Okay? So by putting together this and that, you find that the energies En are, well, do the algebra, you get 2n minus 1/2 h bar omega. And you immediately see that they are, for instance, 3/2 h bar omega. The other is 7/2. Then you have 11/2, and so on. You see that the first level is not 1/2, because that is even. So the first allowed level here is the first excited level, which is odd, 3/2. Then you jump over the next even state, because that's not allowed. And again, you find 7/2, which is the next odd state, which is allowed. Okay? So you see that the classical, the odd state of the harmonic oscillators are exact states of this half-cut harmonic oscillators, and you recover exactly the right energies with this quantization condition. Okay? So in some sense, it is a very powerful tool which allows to explore potentials that would be very complicated in more general case. Okay, I think that this is enough.